So welcome, my name is Leor. This is a C++ 11.14 overview. And this talk has evolved over the past 4 years or so. It's been taught in various lengths. And each time it's just a little different with a slightly different set of constraints. So for today, it's a two-part talk. It's going to be 2 hours long and covering just the language. So we're not really delving into the library at all. Basically just the language, C++ 11, and with some 14 stuff added in as well. The agenda, I'll start with a brief look at the most commonly stolen slide in C++, the C++ timeline. Briefly cover the goals, kind of as a high-level abstract description, and then we'll go into the actual features. And I've organized them into the following set of sections. Part one, the simpler features of the language. Each of them fairly self-contained and doesn't interact too much with the other parts. Part two, facilities for class design, to make the relationships between classes a little bit clearer and harder to make errors that lead to runtime debugging. And part three are the larger features. So that's broken into features relating to initialization, move semantics, and lambdas. So what I've tried to do here, it's a breadth, not depth approach to these features. My goal is to mention every feature that I'm aware of at least once and go into a little more detail on the ones that have a little more meat to them and will impact your transition from old to new C++ the most. Whenever practical, I introduce a feature by showing what a limitation was in old C++, 9803 basically. And then introduce the new C++ 11 or 14 solutions. And I'm specific. If I say 11, it's available in 11, and if it's 14 only, it'll be labeled as such. So the code's been tested, but it won't run exactly as you see it on the screens because I've left out things like includes and standard and usings in order to make the text easier to see. So if you imagine all those things were in there, it should actually compile. So it's always nice to start with kind of a bird's eye view of where C++ has been. First standard, C++ 98, of course. And the point that I think everybody at this point is pretty aware of is that there was no major language update until C++ 11. It was a bug fix version, C++ 03, right? So the point of this slide is that the committee decided it's not really a good thing to go this long between revisions and introduction of new facilities into the language. So from this point forward, the increments will come more often with a little bit less overwhelm in terms of the number of features that are introduced for each of these. So C++ 14 is almost set. We all know what's going to be in it. And it's considered a minor release because it's really a completion of the vision of what C++ 11 was supposed to be. As usual, the committee runs out of time sometimes and has to defer some of the features. So 14 will be kind of a completion of that, and then with 17, there'll be new major features, but not as many that were major in C++ 11 as opposed to 9803. And the same sort of thing's happening with the libraries and other, both language and library subsystems. Instead of there being just kind of one official standard committee action, the TR1, which we now call it the library TR, but that was TR1. That was a significant publication of the interface for new facilities in the library, which allowed the community to learn those facilities and get comfortable with them before they were officially standardized over here. Now there's going to be a lot of these little TRs, now called TSs for technical specifications. And Pablo this morning in his talk had a great term for these, called them sort of pseudo-standards. So they're not official standards yet, but they're as close as a document can be to the official standard without actually having it ratified by the entire committee. Of course, you realize the standards committee is an international, it's like working on an international treaty because of all of the politics involved. So that's why those things take a long time. So all these facilities will be published and folks can start working with them, and then they'll be standardized somewhere out here. And that's sort of the transition of how things work. Goals for the new C++. Make C++ easier to teach, learn, and use. And it succeeds on all those levels. The one as a as a trainer and a C++ educator, the teach one was pretty exciting to me. The feature that was supposed to primarily facilitate that was concepts, which was dropped from C++ 11. So even without concepts, I believe it still is easier, but not as much easier as it will be when concepts finally ends up in the standard at some point in the future. Maintain backwards compatibility, of course, that's always important. You don't want to break existing code bases. And for the most part, they've done a pretty good job there. There are some breaking changes, but again, when you look at the specific cases, it's code that probably should have been fixed for other reasons, and the fact that C++ 11.14 breaks it is not that big a deal because it's not great code in the first place. I think that captures the majority of cases that it's not actually backwards compatible. Improving performance is always a good thing. Strengthen library building facilities. That's the features for class design. Allow a programmer to be a lot more explicit in the relationships between types. So a whole bunch of errors that the compiler would not be obliged to catch in old C++. It now can catch if you empower the compiler to do that by using these facilities. And the last one, interface more smoothly with modern hardware. That's really code for concurrency. Right? Modern hardware is moving to multi-core environments, and the language now supports that directly through standardized concurrency, multi-threading, etc. So those are kind of the major goals. Lifted this little tidbit from Bjarne's FAQ on C++ 11. The pieces just fit together better than they used to, and I find the higher level style of programming more natural than before, and as efficient as ever. A little understatement there because it's actually more efficient than it used to be. All right, so this is what we're going to cover in part one, the smaller features. Instead of telling you what I'm going to tell you, I'm just going to tell you we're covering those. Let's look at a piece of old C++ code. So this is a function template called find null. It's not an algorithm, right? Can you look at that and sort of say that that doesn't count as like an STL type algorithm because it doesn't take a pair of iterators. So it's just a function template that takes a container of some kind and it assumes that it contains pointers and it returns an iterator to the first null that it finds. Or if there's no nulls, it returns end, meaning the end of the container, which is the STL convention. So in old C++, we need a return value. What's the return value? What's going to be an iterator type? Given we have a container, we can derive the iterator type by knowing there's a nested type called const iterator. And we'll use const because we're not intending for the client to make a change. We're just locating a value. So const iterator is the appropriate type to return. And then we have to throw this type name in. Whoa, am I dizzy? I got more sleep than that. So how many of you, just to give me some idea, how many of you know why you have to put the word type name here? And how many don't really know, or you may have seen it and you forgot? Yeah. So unfortunately, in old C++, this is stuff you have to understand, or else you get compiler errors. Name of a nested type inside of this type of cont. But cont itself is a template parameter, so when the compiler is compiling this code the first time, when it's seeing that code for the first time, it doesn't know how it's going to be specialized. It doesn't know what type of container is actually going to be passed in here when the client calls this thing, specializes the template. So the compiler can't possibly know within this type cont what const iterator actually is. It's just a name here, and we know what's in the scope of that thing. So there's two possible things it could be. If that's all you know, it could be a name of a member, like a static data member, for example, or it could be the name of a type. Well, data members and types are used in completely different statement syntax forms. They're not interchangeable. So the compiler has to be able to make a choice of whether this is supposed to represent a type or it's supposed to represent, say, a static data member. And the language rules actually stipulate the compiler must assume that's the name of a static data member by default. So if I didn't say type name here, the compiler would assume this is the name of the static data member, which is of course wrong. And then based on that, this would immediately become a syntax error. In the early days of C++ 98, compilers tended to forgive this error because they just read the mind of the programmer and basically put the type name in for them. And that was actually a disservice because code would pass the compiler and actually work. And later when compilers got a little more strict about this, that same code would yield compile errors when it was wrong in the first place and shouldn't have been passed. All right, so that's the story. Listen to how long it took to explain that. The return value is going to be an object of that type, so again, I have to repeat that. Yeah, I could use a type def or something, but considering I have to name it first up here, a type def really wouldn't have saved the keystrokes. It would have been actually more keystrokes. Then I do pretty much simple loop looking for that value. When I find a null in there, then I break out a loop and I return the iterator to it. And if I never find it, then it ends up equal to end, and I return that. So that's my C++ 98, old C++ find null function template. How would I use it in old C++? Well, first, I have to throw some data into a vector. So I define my vector, let's make it of int pointers, and here's a bunch of ints, and I throw their addresses in there, and then I put my null in. So quite a bit of rigmarole just to stick some simple values into a vector, but that's what it used to take. Okay. In real life, a lot of the time, you're not pushing back known values, you're computing them and all that, in which case the code doesn't look so awkward. But first, the simpler the example, the more awkward it ends up looking when there's no simple syntax for initializing a vector with a bunch of values. So the client here is going to call the function, capture the result in a variable. What's the type? Well, it's a vector of int star const iterator. Pop quiz, why don't I have to put type name here? We're not in a template, therefore it can't be a dependent type. Dependent types only happen inside of template code. So that's holding our variable. If it's the end iterator, there were no null pointers. Otherwise, now we found a null pointer and we'd like to display the index position of that null. If it's the second one in there, it should display index number 1. Sounds simple. All we do is we subtract the begin iterator from the iterator that came back from find null. But what's the type of something like that? Chances are you would type size t as, I'm sorry, size t, is that right? Yeah, size t as the position. And it would probably work. It would probably work. But technically, that's not kosher. Officially, the type of subtracting two iterators is the difference type, which is another nested type in the class that the container producing these iterators has. So to be completely legit, I need to declare pos as a vector of int star difference type, and then I can display the value. So I'm going to start by showing the C++ version of that slide we just saw. How would we adapt C++ 11 features to use find null? First of all, thank goodness, we can just brace initialize the vector. Thank you. I actually wrote a library that sort of made up for the lack of this for people taking classes, learning about the STL for the first time. To be able to just stick a bunch of values into a container was such a pain that I actually wrote a little template library just to do that. And now we can just do it in the intuitive way. Good. We like to obsolete things that should never have been necessary in the first place. What does find null return? We don't have to know. The compiler does. Of course, in C++, you can't call a function until it's been declared previously, right? That declaration could be the form of a definition or just a declaration, but the compiler must see that or it's an illegal call. So we know if this compiles, this call even compiles, the compiler knows the return type. Why don't just let the compiler plug in what it knows? That's what auto says in this context. And it just figures out, it deduces. Of course, you all saw a whole lot about that this morning from Scott, right? So first new feature. All right, nothing different here. Now, if we want to display that index position, again, instead of having to know about difference types, we just subtract the iterators and stick an auto on there, and it figures out that's a vector of int star colon colon difference type. And it just works. All right, we'll return back to find null shortly. Take a little bit of a detour here. Here's a function template that's impossible to write in C++ 98. It's called product. It returns the product of two values of unknown type. What do you put for this 3 question marks? If you know nothing about these two types, there's no syntax to properly stick a type in here that's going to represent the result of that multiplication. Right? If T and U are the same type, we could just pick one, but if not, we just don't know. And what if T and U are matrix types, right? The result of multiplying 2 matrix might be a type that's not either of the 2 original operands. It's some different type. Yeah, no way to do that. So new C++ offers a solution. It's a different use of the auto keyword. So in this case, auto is not deducing anything. Auto is used in conjunction with a syntax called trailing return type. And that may be a familiar looking token. That's not a coincidence. The committee likes to reuse existing keywords and tokens. So this means I'm going to supply the type the function returns back here rather than up here. The benefit of that being, once we get to this point in the translation, the compiler now sees the declarations of T and U, and you can use those in the specification of the type of the return type. What's the type that this function returns? It's the type you get when you multiply T and U, where T and U are the function parameters. That's it. This generates no code. This is a compile time operation. It evaluates that expression internally without actually generating code, purely for the purpose of determining the type, and then we can use that. This part of the code doesn't have to be a decltype expression. It could be like int, and it's legal, but that would be kind of silly because you could just put int up here, right? So usually you'll see trailing return type used in conjunction with something like decltype, which says, what is the type of this expression? The syntax of decltype is similar to the syntax of size of. If you recall, size of has 2 forms, size of a type, size of an object. One of them you need the parens, one you don't. If you can't remember which is which, just always use parens, and it always works. And basically the same rules apply to decltype in this context. Just always use parens. Right, so now we can take a look at a new C++ version of find null. We'll leverage the trailing return type here, and we can pick cbegin, cend, whatever. They both return the same iterator type, whichever strikes your fancy, and that's the return type. And nothing else in here yet that we have to talk about, but we will shortly. So in old C++, begin and end were member functions. That's what they were. In new C++, a non-member style of begin and end was introduced, and it allows things to be written a lot more generically. So let's say we have a function called string length greater than 4 that takes a C string, returns if its length is greater than 4, and we want to apply it to a find algorithm call. Actually, we're not applying it yet. So here's a find call that just searches through this vector, this container, for some value. So this is the non-member begin and end. And you look at that in and of itself, and it's, well, okay, we've saved the keystroke, right? And that seems to be about it. Well, that's good, unless you're paid by the keystroke. But that's generally a good thing. Make the code a little bit cleaner. All right, so here it is being used again to determine the end iterator of the vector. But you still have a choice of using the old or the new form of begin here. We could have said v.begin open close. That would have been equivalent, 100% equivalent. But now, the non-member form actually works with things like built-in arrays. as well. And there is no equivalent member version of that for a built-in array. You can't say names dot begin, open, close. That wouldn't compile. But if you have this old C-type array, you can say begin its name, end its name, and it gives you a pointer to the first element and a pointer past the end. So here's the end pointer being used again. So you can see the generality of that, right? Old C++ had 4 types of iterators, right? A regular iterator, a const iterator, reverse iterator, reverse const iterator, but only provided begin and end, which returns one type of iterator. C++11 adds cbegin and cend to immediately give us a const iterator without having to jump through hoops to get that for, say, a non-const container. And rbegin and rend to get the reverse iterator corresponding types, and const reverse iterators we can get with crbegin, crend. So here's why this is useful. So in C++11, oh, this is a C++14 feature, sorry. So these were added for 14, actually. So in 11, if you have a container that is not a const container, and you wanted to get a const iterator for it, you would have to actually declare it explicitly, and then the appropriate conversion would happen. In C++14, you just say cbegin, and it knows you want a const iterator. So it saves you from all that typing and having to put type name in. So yeah, so this is a 14 only feature. All right, back to old C++ and C++11. So the concept of a null pointer has gone through a lot of evolution over the years. They had them in C, right? A null pointer was any pointer equal to 0, or NULL. But we don't really know how NULL was defined, and it was sometimes defined in different ways across platforms, so that code that worked on one platform might not work on another. It might be an int or a long. At some point, I think some platforms may have defined it as a void, a zero cast a void star or something. There was some nebulousness about its type. And if you're reading somebody's code and you see a 0, do you really know, without thinking carefully about the context, is that person thinking null pointer, or are they just thinking the value 0, right? It's not always obvious. So there's some imprecision there in that syntax. Here's 2 overloads of a function f, one that takes a long, one that takes a pointer to char. If you specify your argument here explicitly as a long, it clearly binds to that. But if you say 0, this is an error both in old and new C++, because 0 converts to both long, or any integral type, and to a pointer type, right? So the compiler doesn't try to read your mind about which of those you meant, and it's a compile error. Right? Nature abhors a vacuum, and C++ abhors ambiguity. So you'd have to do a cast. And once you did that, then the compiler was happy. New C++ introduces a new keyword, nullputter, which acts like an object that is a null pointer, and only converts to pointer types, but not ever to integral types. So using nullputter in the place of 0 is always a good thing when the 0 is intended to represent a null pointer. It's only going to improve the quality of your code. So as before, given the same 2 functions overloaded, if we pass 0L, it still binds to the long. If we pass null pointer, it binds to the char star, completely fine. If we say 0, it's still ambiguous, and that's a backwards compatibility issue, right? You want things like that to work the same way as they used to, but if you start moving to using nullputter instead of 0 here, then you leverage that facility. So here's the final C++ 11 version of find null. I just replaced these with non-member versions of begin and end, and then I replaced the 0 with null pointer, because after all, I'm checking for a null pointer. Usually I mention this in case anybody's confused by the fact that I'm dereferencing it, and we're still looking at it as a pointer. Remember, this is a container of pointers. The iterator then is like a pointer to pointer, right? So the dereference here is on the iterator. which gives us the underlying type, pointer to something. And it's that we're checking against null putter, just in case anybody was thrown by that. C++14, as Scott talked about earlier, adds function return type deduction, and that allows us to simplify this a little bit more. We can just say auto and then return whatever, and the compiler figures out what the type is and plugs it in there for you. So that's C++14 only. Now there's actually two ways, right, to do the function return type. We could say auto, as in the last slide, or we could use decltype auto, and Scott talked about that this morning as well, so now you've seen it again. If it uses plain auto, then its template type deduction rules apply. So for example, you couldn't return an initializer list. It wouldn't compile in that situation. If you use decltype auto, then it uses decltype type deduction, which is an exact match for the type of the return expression. And so Scott talked about some of the situations where you might want one or the other. Just pointing out that there's that choice. And a lot of the time auto is fine, and when it's not, decltype auto might solve the problem. All right, let's move on to iteration. So old C++ code for iterating across a native array. Here's a native array of ints. Now notice I've defined this by providing a brace initialized list of values. And the flexibility of something like that is you can go in and change the code by adding a few extra values at some point, right? Without wanting to have to change anything else, have the program just work. And the traditional way of dealing with that is kind of a hack like this, where you take the size of the whole array by the size of one of the elements, and that's the size. And now if I add an extra value or two, this will automatically adjust, and all the other loops will work correctly. And then I use that size as my loop limit. So here I'm going through and just displaying every element of the array, and then I'm initializing a list from all the elements in that array. Then I'm going through and doing something, adding 100,000 to each element using a loop, and then going through and displaying all the elements from that list. So the idea here is these are pretty straightforward types of operations. Iterate through all the elements of a container and do something. But there's all these potential spots for error here. One little slip of the finger, and you've got off by one conditions and potentially undefined behavior. Right? It's a very, very simple thing you're trying to do, but it takes kind of a lot of rigmarole in order to express it. So that was addressed in new C++ with the range-based for loop. It's not a silver bullet that will work to eliminate all for loops. Okay? There's situations you still have to use for loops for, but a lot of them can be cleaned up by using the syntax. So if I have this array or a container, I just say for auto I read that as in, for auto I in AI. And in this case, it's going to take each value, copy it into I, and then you have access to that variable through that iteration, and the compiler takes care of that. If it's a type that's expensive to copy, which ints are not, but if it's a widget or something that's 10,000 bytes worth of payload, and you don't want to have to copy each element into the loop variable, you can put an ampersand in there. You can decorate this thing with auto-ref. So this tells the compiler, I want this to be a reference. So now each time through the loop, we've got a reference to that corresponding element, and we can do things like modify it. Right? Got to be careful. If you don't put the reference in and then you try to modify, you'll be modifying the temporary, and then it'll get thrown away. So you've made no change to your actual data. Not the one you're going to see at the end of the loop anyway. And you can have constants in there as well. So you can decorate these all any way you want. And you don't have to use auto. I use auto in the examples to try to support auto as a good idea. But yeah, you could certainly have just used the exact type and it would work. Or you can even choose a different type and it'll do conversions. But auto is kind of this path of least resistance for this kind of thing. And just to throw in a curve, you can even have this initializer list here as the set of values to operate upon. And that works. It'll properly display each value. So I haven't introduced those yet officially. It's kind of a teaser. All right, so that's the range-based for loop. Oh, I mentioned there's cases where you can't use it. If you need the value of the loop variable after you exit the loop, it's not going to work for you. So it has to be the case that that variable is only useful in the loop body itself, and you can't need it once you're out here. And you can have a variable you declare out here, and in the loop you can assign it over or something, and so you can see it outside. But the scope of that variable is limited to inside the loop. And in all the times I've used range 4, I'd say about 30% of the time I've been bitten by that and couldn't use it because I just wanted to keep it simple, and I wanted that variable visible outside the end of the loop. Okay. Well, here's one that's pretty easy to describe. You used to have to put the space there, now you don't. Any questions? Good. Yeah, it took a while. So how many are familiar with the assert macro, the old C library assert macro? Right? That's a runtime test for some condition you expect to be true. So in C or C++, you can assert and put in some logical expression. If at runtime that expression is true, it evaluates to true, this becomes a no-op, aside from the code to actually perform the test, but nothing happens. If this assertion is false, then it actually stops the program and prints a diagnostic with file name, line number, and the text of this assertion. And this is actually a macro, so it'll print this exact text and say assertion failed. So that's a very useful debugging feature. And it has the additional benefit of a single symbolic definition on the compiler command line or at the top of some header file will make all assertions turn into pumpkins. They just go away completely and have no overhead, no code, no runtime, no nothing. So in debug mode, the assertions are usually active, and then right before you release, you flip that flag, end debug, right? And all the assertions go away. Then, of course, you get different behavior, and you go, oh, my God. But if that doesn't happen, you're good. There's been no compile time equivalent of that until now. So new C++ adds the static assert, and that allows us to make these assertions that are active at compile time. And we can simply have an error generated if an assertion fails. And then you can go and modify the code accordingly. So the syntax is static assert, your condition here, which must evaluate to a bool and be composed of nothing but compile time expressions. So things like constants and symbolic constants and const expr expressions, which we haven't talked about yet, can go here. And if the compiler reaches this point and this thing is true, it's a no-op. If it's false, it spits out a fatal error at that point. But then it keeps compiling. So there could be many of them that show up in a single compilation. And you can deal with them all at the end of the compilation, as opposed to the runtime, which is one that gets triggered and everything stops. So this can be a productivity boost. In addition to giving you functionality you didn't have, you can also accumulate a whole bunch of them to fix all at the same time. And they'll all show up during one compilation as an error message. So let's look at some useful applications of this, some use cases. Let's say you want your code to only be compiled on platforms that have, that are 32-bit platforms. So you can nip that in the bud by just asserting that the size of an int is at least 4. As long as this is true, it's silent, nothing happens. If this is false, you get an error message with that diagnostic, and compilation is aborted, or linkage is not performed or whatever. Here's another kind of interesting example, and this is an adaptation of a technique that I learned from Steve Dewhurst first in an old C++ environment. As he wanted to illustrate how you'd write a little function template that'll perform a conversion, but it would flag a potentially erroneous conversion with a fatal runtime error. Well, that's useful, but it generates all this code at runtime. Now we can do it at compile time. So the syntax is safecast. So this is an attempt to safecast from whatever the type of lval is to the type int. And if that can be performed safely, we know it's always going to succeed no matter what the value of lval is. It does the cast. Otherwise, it should be a compile error. And this gives us that result. So there's two template parameters here. One for the result, which the client always has to specify, because it can't be deduced from anything in here. And one is the type of the expression being passed, which the compiler can deduce from the call. So when I say safecast to int of lval, the compiler deduces the type of E is long, and we've told it the type of R is int. So then it performs this static assert. If the size of R is greater than the size of E, greater or equal to, then we have a potential problem. No, I said that backwards. As long as the size of R is greater or equal to the size of E, we're good. And if that's not true, we have a potential problem, sorry. And if we get past that line, then we know we can do this cast safely. So there's a couple of nice little uses of static assert. All right, object file code load. So normally I spend a lot of time talking about this because it's an interesting story. So I'm going to try to laser today so we can get through everything. To process include files, or to process templates, sorry, there's basically two ways to do it. And the industry has settled upon the approach that everything in the kitchen sink is in header files and it's all compiled at that particular moment as opposed to having separate compilation. So every translation unit includes the full header for all the templates that you're going to be used in that translation unit. The problem with that is that a lot of the time, the functions that are actually instantiated are duplicated across translation units. If you have a large code base with 1,000 source files and you have a template like vector that you use everywhere, how many of those modules use pushback? Probably a lot of them. You have all these redundant instantiations of vector of int pushback. Then the linker, knowing that that's the way the code was generated, ends up throwing all of those away except for one. It seems it would be better if there was a way for the compiler to only have to instantiate that vector of int pushback function one time, even across a large code base. So that was the problem. And the solution that didn't work very well was called export, and it was excised from the standard. And that's all I'm going to say, because you can get me started on that. The right solution is extern template. I'm not sure if anybody thought of that earlier. It would have been great if they thought of that before export. But anyway, presume most folks are familiar with extern on ints, for example, right? You say extern int I, it means I is being defined somewhere else. And I can use it here, and it'll link with the actual definition in some other module. This concept has been applied to templates. So we include the template header file as before in old C++. And then we take the specialization that we know is going to be used in a lot of different translation units, and we declare it extern. Extern template class vector of widget. What this tells the compiler is do not instantiate any member functions of vector of widgets. Just assume they'll be instantiated somewhere else. So if you've got 1,000 modules in your application, all 1,000 will have this statement, because this is in a header file, basically. And then one source file, one CPP file somewhere will say this. So it's already seen this stuff, and then the compiler sees this line of code, template class vector widget. And this is not new for C++ 11. This is just explicit templates instantiation. It tells the compiler, generate all the member functions of the template vector for specialization of widget. And they're all generated right there in one place only. And then the linker will still discard the ones that aren't actually called anywhere. So when the dust settles, you get the same exact code that you had in C++ 98, but you've wasted a lot less compile time and disk space and link time to get there. And that's extern template. It's very elegant, I think. All right, so old C++ had these dynamic exception specifications. So they weren't called that back then. In 98, they were just called exception specifications, because that's all there was. And it lets you specify what exceptions a function might throw. There's some languages where that's actually useful, that feature. Java, for example, if you have a specification of the exceptions your method is going to throw, the compiler enforces that. If the caller doesn't somehow take note that there might be a foobar exception thrown, it won't even compile. But that's never even been true in C++. I can specify 2 or 3 exceptions I'm going to throw here. The caller of this function doesn't have to even think about that. The code will compile. So there was kind of a limited usefulness of exception specifications in the first place. Then when templates were added into the mix, exception handling, I think, was come up with a little before templates. With templates, it's impossible to even specify what the exceptions a member function of a template might throw, because we don't know what the type T's member functions do or what kind of exceptions they throw, because we don't know what T is yet. Therefore, in the C++98 standard, the only type of exception specification you ever see is the empty one, because it is useful to say, I'm not going to throw an exception. And if you know something about this mechanism, you know that's not even what this really means. It doesn't mean an exception will not be omitted from swap. It means if code inside of swap tries to omit an exception, then that will be translated into an exception that says that exception. It's still going to propagate an exception. So the whole thing was kind of ticky-tack and not all that useful. The real usefulness of the empty throw specification was for optimization purposes. The compiler can generate code, take advantage of the knowledge that we're not supposed to throw an exception and generate some better code. But the whole thing wasn't very well. It didn't evolve very well during early C++'s evolution. So taking that all into consideration, the newfangled way to deal with exception specifications is the word no except. Basically is the moral equivalent of throw, open, close. I'm not throwing an exception, but it's simpler to implement. And that helps the compiler know that the code that calls this function can be optimized with the knowledge that it's not going to legitimately emit any exceptions. Ironically, if you do throw an exception out of here, it's not illegal, it'll just terminate the program. So, I mean, it's not illegal at compile time, and at runtime it'll terminate. So that's not quite the end of it. Sometimes it's difficult to be able to say whether a particular member function is going to throw an exception or not, because it's really dependent on the exception throwing behavior of the functions it's calling subordinately. There's a way to express that. So if you're familiar with the pair struct, well, it's a class, but it's used to hold elements of a map, as well as other things. If you have this pair class and you want to supply a member function for swapping, and the types that make up your pair are T1 and T2, and you don't know anything about their characteristics, how can you promise swap is going to be a non-throwing operation? For all you know, the member function swap of the first type T1 and the second type T2 might throw. So there's a way to deal with that. And this is called conditional no except. So it's no except open paren, close paren with a Boolean expression in the middle. If that Boolean is true, then it's like saying no except. And if the Boolean is false, it's like not saying no except. And you can make this thing's no except be conditional on the no except status of swapping T1s and swapping T2s. So this is actual code with some of the clutter eliminated out of a G++ header file I found on my machine to look for a real-world example. So you get the idea why that can be useful? It can be complicated. The syntax is not as pretty as it might be. The no except, it seems there ought to be some cleaner way to say that, but this is what we've got, and it works. All right. Next problem. Let's say you wanted to write a function to find the average of a bunch of values. You don't know how many the user is going to want to supply. Well, even in C, there's a way to do it. It's called variadic functions, right? What's the poster child for variadic functions in C? Printf, the whole printf family, right? So this tells the compiler in C there can be 0 or more arguments passed. There's one required argument that's an int, and there's no requirements on how many additional or what their types are. And then there's an interface to actually access the values of those types, as long as you know what the values of those arguments, as long as you know what type they're supposed to be. So that's the problem here. There's no compiler checking for those types. And if the user supplies, the first parameter here is the count, right? If the user actually only supplies fewer numbers than the count, there's no way for the compiler to know that, and you'll end up with some undefined value as a result of that. So you have to write one of these for each type, which is pretty bad. You have to provide the count, which you might mess up, and no type safety. So that's one approach that's the C-like approach, not very good. Another, we can use default arguments. Well, not really. For certain functions, maybe, like for a sum function, Yeah, but not for something like average, because a function in C++ cannot ask how many arguments were actually provided, even if there's some that are defaulted. There is no interface for that. So you can't do an average if you don't know how many values were provided. So that won't work. There's some combination of overloading and templates that might solve the problem, but it's going to be ugly. So let's see if there's a better solution. Well, C++ 11 does provide it. It's called Variadic Templates. Variadic templates are a little bit mind-blowing if you've never seen them before. Think of the classic example of calculating the Fibonacci number recursively or something like that, except it's a compile time mechanism involving functions, but instantiations, rather than the calculation of a Fibonacci number. It's a recursive mechanism. So in any recursive mechanism, you have the general case and then the terminal case, right? For Fibonacci numbers, the terminal case is the first or second Fibonacci number has a known value. The general case is Fibonacci n is the sum of n minus 1's Fib n minus 2. Variadic templates have the same structure. There's a terminal case, which is the simplest one, and then the general case that we don't know how many arguments are provided, but eventually it devolves into the terminal case. So to do average, first we need to do sum. We're going to spend most of our effort here to figure out how to do sum. And once we've got sum working, average is easy. So how do we do a sum of some unknown number of values? Sum of 1, 2, 3, 4, 5, 6, 7. So this code correctly calculates the result of this expression. This code, all this together, correctly gives you the result of that expression. Notice some things here. All the types are the same. Now, there's nothing about the way I've written that requires it for the compiler's point of view. But for correctness, we'll see how it won't work if you mix types. But this just gives you the initial simple case. So how does this work? So this is the general case that's tricky. There's a special syntax, type name ... This is called a template parameter pack. And then there's, in the function header, there's the name of the parameter pack followed by ... And this becomes a function argument, a function parameter pack. Parameter packs, the template parameter pack and the function parameter pack work as a matched set. They're synchronized. So they go together. You can't have one without the other. There's no syntax for that. They always go together. And think of it as a whole set of arguments of different types. The first one has type args, and it has a value. The second one has type args, and it has a value, and so on. But they can be different. Down here, if we use the name of the function parameter pack with 3 dots, that expands to that list of all of those parameters, their type and their value. So if we have this case here, this turns into sum of int n and all the rest of these, which is from 2 to 7. And then it recursively unwinds until it eventually gets to just 1. And all this happens at compile time. The generated code for this is the same as if you threw the number, which is the sum, into a register and displayed it. Right? There's no calculation, there's no addition, there's no recursion at runtime. So it's all a compile time process here. So those two work, great. But not really so great. If you mix types, we run into a problem. Because notice that the return type of the terminal case is the type of, or of any case, is the type of that first argument. So if we have something like sum of 1 and 2.3, we're locking the return type to be an int. Not very healthy. We're not going to get the right answer. So that's, at this point, it's a logic bug in this approach. It's going to yield the wrong value. It's not a compiler error. The compiler will happily compile this, and it'll give us the wrong value. So you'd think we can solve the problem using trailing return type and auto. So here's the correct approach. The return type of summing all this stuff up is the decltype of summing all this stuff up. So here's the expression that calculates the sum. I just want its type. Makes great sense, but it doesn't compile. And the reason it doesn't compile is a little bit of a surprise. The recursive reference to sum is illegal because the compiler doesn't really know the type of sum yet. So if we go back here, how can it determine the type of all this if it doesn't really know what, it's a chicken or egg problem, and the compiler rejects that, and you get a compile error. The next surprising twist is that this restriction is lifted if the function name is a member function. If it's a member function, you can get away with that chicken and egg problem. So all we have to do to make this work is make sum be a member function. And if we make it a static member function, it'll have the same behavior of a non-member function. So all we do is wrap this stuff in a struct, and it compiles and works. This is the way the language is specified. Don't ask me why. I've never been able to get a straight answer about that, and I've tried. Somebody knows why this is. So this is the workaround.
Because the static function is just like the same as a standalone.
So the question is, the static is the same as a standalone? Yes. For all intents and purposes, the same code is generated as if it would have compiled as a non-member function. But because the language stipulates you can't do that in a non-member, but you can in a member, you just make it a member and it works. Okay? Don't shoot the messenger. This is just the way it is. All right, well now doing average is easy. We finally got a sum that works. So to create the average of this set of values, we can specify the return type as the same as the type of the sum, right? Because all we're going to do is divide the sum by the number, and we're going to keep the same type. And then we go ahead and we calculate it. But we need one more little twist, which is how do we know how many items were in the parameter pack? Well, fortunately, the language gives us size of ... is a special size of that applies only to parameter packs, and it gives us the number of items as opposed to the amount of storage taken. So it's a special form of size of that's designed exactly for this purpose. Question?
Will that use integer division always, or will that be smart enough to?
Question is, will that use integer division? No, it'll use the appropriate division for whatever this type is and an integer. So if this was a double, it's going to end up with a double. It's a double over an integer. If this is a unlimited precision int, the result is an unlimited precision int. So it's just normal conversion rules apply here. So now we can mix up. It's average works when they're all the same type. It also works when they're all different types, which is good. Of course, there's a caveat. It must be possible to add these together. So if you put a string in there, a standard string, it's not going to compile. Or will it? No, you can't use plus on a standard string in an integer or a long, so that won't compile.
What if you run an operator function?
If you wrote, the question is, what if if you provide enough overloads to make all your cases work, of course it'll work. But just given the standard string interface, no, it won't work. Okay, so we know about const. Const has been around for a long time. Here's a simple constant called size, and it can be used in situations where a variable can't. For example, as an array dimension. So WArray is an array of this many elements, and that's fine. What if we want to compute a dimension for an array? Unfortunately, if it's something that's truly a runtime variable, like val down here is a runtime variable, you can't use that as an array dimension. But C++11 introduces const expr functions. A const expr function acts like a whole bunch of different functions depending on whether the parameter passed is a constant expression or not. So, okay, this happens to be a template. But even if it wasn't a template, you can still have a const expr function that will behave differently depending on whether its argument is constant or not. If it's constant, it's compile time evaluated, and the result is a compile time constant. If the argument is not a compile time constant, it turns into an ordinary function, and then the return value is not constant. And that determines what you can do with it. So square of a constant is a constant, and that becomes fine to use as an array dimension. Square of a non-constant is fine to put into a variable, but it's not fine to use as an array dimension. So that's const expr functions. The const expr functions have evolved from C++11 to C++14. So in 11, the bodies of those functions were limited to just a single expression, and you couldn't have if-elses or loops, although you could simulate them. In C++14, a lot of those limitations are relaxed. You can now have multiple statements in a const expr function, and it works. So Bjorn characterizes this as roughly a const expr function now, we're talking about 14, can contain anything that does not have side effects outside the function. And you still can't do goto, you can't have exception handling, you can't call non-expr functions, etc. But it does give you more flexibility of what you can do in there. How are we doing on time? Getting pretty close. So let's see if I can do the next 6 or 7 slides here. Template alias. There was an omission in the template declaration mechanism such that there was no way to specify that I want to be able to declare a template that always has a specific template parameter, say in the second position. So there was no way to say I want something that acts like a set of t that always uses greater as the comparator. And now there is. So by saying using setgt, and then supplying this with a specific second parameter, a client can now shorten that to say, can just say setgt of double, and it automatically puts in standard greater of t as the comparator. So there were several different proposals to do this. This is the one that ended up getting used. And it used to be called template typedef, but rather than making typedef be the syntax for everything, it's kind of gone the other way. And using has become the syntax for everything, and it even replaces typedef. So instead of declaring a pointer to a function this way and typedefing it, now you can say using void func equals. And I think this is actually clearer. Right? And imagine if this was a lot more complicated. Have you ever had the situation of looking at a typedef and trying to find the identifier to know what it is that's actually being declared there, right? So that goes away by using, and then you just put the name of the identifier for your typedef. So these are equivalent. So from going forward, you can stop doing this and just start doing that, and it works. All right, so now it's just some miscellaneous things. I'll probably cover these in a minute. Unicode strings of different kinds. Raw string literals. This is really handy in conjunction with regular expressions, because now there's a regular expression library. So instead of having to look real carefully at all of your backslashes, you can just say r quote open, have anything in here be literal exactly as you write it, and then close quote semi. So this is the opening and closing delimiter for that. And that covers every possible set of text you can put in here except for one. The one that would contain a close quote, right? So as long as if you don't want a close quote as literal, then you're fine. But if you do, then there's an alternative syntax where you can specify an arbitrary delimiter that you put at the beginning and the end. And that can be up to 14 characters long, which I think should cover just about everything. So, string literals. Inline namespaces. It's always been a little tricky to try to revise libraries and make it user-friendly. Clients have to go in and change their include statements and that sort of thing when a sub namespace has been updated. So inline namespaces provide a default namespace within another namespace that is hoisted up into the parent level implicitly. If this is my company, BD and I'm supplying these 3 versions of a library, this is the one that people are currently using, and this is like an experimental version, and this is an old retired version. And when I evolve it to the next level, I'll simply move the inline from here to here and ship it. Client code does not have to recompile. It just works with the current version. I'm going to skip this over. We're running out of time. I want to just give me another 2 minutes. Okay, I just want to cover the rest of these because they won't be at a good stopping point I was planning for. So like I said, I wanted to at least mention everything. Scoped enums or enum classes. have a bunch of benefits over the old enums. Their enumerators don't leak into the surrounding scope. And you can specify the underlying integral type if the default, which is not something you could ever control, is not appropriate. So that's scoped enums. Long is a new type that's official. You can control and query boundary alignment for various types. And Pablo gave an example of that in his talk this morning, if anybody attended that. Generalized unions and generalized pods kind of go together. Unions and plain old data types had a bunch of restrictions, like they couldn't have constructors and destructors. Well, they realized you could still let them have constructors and destructors without breaking any of the constraints for what these things are used for. So now they can have constructors and destructors. They still can't have things like virtual functions and all of that. But the restrictions have been significantly relaxed in C++ 11. There's a garbage collection interface. There's hooks for a garbage collector, but there's no actual garbage collector provided, but at least it provides the opportunity to build one in a standard way. User-defined literals. If you wanted to have a binary type and you wanted a B to be a way of users writing a literal, you can actually program that to be legal code. And it's all kind of a hack. It basically passes this as a string to a constructor you provide, and then you provide the code of how to do the conversion. In conjunction with const expr, it's very efficient because these. Beg your pardon? No underscore. You might be confusing that with this with literal binary. Are you?
When I had to write my user-defined literals class,
Yeah.
my process should be using underscore for the B. So binary B equals binary G underscore.
Really? Okay. I'm not familiar with that, so I've just never seen it. The question had to do with, do you need to put an underscore here?
No, that's not.
No.
Before B.
Over here, under bar B. Okay. Again, I guess I haven't looked at enough code. I thought I took this out of an example. Maybe not. Okay, so in 14, there's also official binary literals. It's kind of funny. I used this example of binary, and then this slide was added later, where now there's a way to do binary literals that's built in, right? So you wouldn't probably need a user-defined binary type. You just, or at least you can specify binary values. That's what this is about. And you can also use a slightly displaced comma inside of numerical values. It's an apostrophe. Lets you read the numbers better. All right, that's where I wanted to stop. Great. So we'll be continuing at 3:15.